Hello, so in this tutorial I'm going to show you how to download the test case from the OneDrive storage space and then use it to test whether the installation of OpenFOAM 6.0 and GetSafely was successful. So now let's click on this link. So here is the storage space where the test case is stored. So here we can see that there are two folders, and the second folder is where the test case is stored, and the first folder actually has got some results that you would get if your installation was successful. So once you've run your test case, you can then compare the results your simulation created with the results stored in this base case folder. So if they are fairly similar, if not exactly the same, then you're confident that your OpenFOAM and GetSafely has been installed properly. So to download these two folders, you have to click on this to select them all and then click on download. And because these files are actually quite large, about 1 GB, and it takes a while to download, so I've already downloaded them to my computer. Here you can see them. Okay, so now let's go to the user guide and then follow the instructions here to run the test case. So as I said in the first video, there are two blocks of instructions and comments. So the first block is for single thread simulation, and the second block is for multiple thread simulation. So in this tutorial I'm going to show you how to use the multiple threads simulation. Okay, so let's see what we need to do. So after you've downloaded the test case, you've got to make sure that the MyCheck test case folder is downloaded into the OpenFOAM run directory. So if your operating system is Windows, then you will have to copy the folder across by using this command here. So now let's do that. Copy and paste. Now please make sure that you replace the username in the first path with your own username. I think I explained this in the last video, so I won't explain it again. Let's just replace username here with my own username here. Okay. Now what's the next step? The next step is to first of all go into the go into the case folder by using this command. Okay, so let's use ls to see what's in this folder. Right, so I think they're exactly the same as the folders here, so they've been copied across. Now the next step, as I said, all you need to do actually is just to copy and paste these commands into the terminal and run them by pressing the Enter key on your keyboard. Okay, now let's go and execute the next one. Okay, so it's created some information for us. If you would like to sort of read this information in more detail, if you use ls, we can see that this command here has created a log file, and you can actually open that log file by using vi to see what's inside. Okay, so these log files are very important and useful. If anything goes wrong, usually the error messages are stored in these log files. Okay, let's run the next one. Okay, it's still running. It might take a little while. So whilst it's running, let's have a look at the next command. So I think what this command does is to split the domain into some other little ones. so the computation can be parallel. Okay, I think somewhere here it says let's have a look. Yes, so before you run this command, you can open this file here that says decomposed part_dict file to specify how many numbers of cores to use. Right, so that number needs to be the same as the number used here in the next command. So here we're using 4. So if you would like to use 6 or 8 or even more, first of all you need to change this number in this file, and then change this number as well. Okay, seems like it's still running. Okay, so I'm not very sure how long this will take, so what I will do is I will pause the recording and then come back when it's finished. Okay, welcome back. So it seems like it's finished the meshing. Now let's move on to the next step, the next command, which is the 5th one. As I said previously, before you run this command, if you would like to use a different number of cores rather than 4 cores, you will have to set this variable here within the decomposed part_dict file to make sure this number here is consistent with the number you're using in the step after. So the question is, where is this decomposed part_dict file? So now let me show you where it is. So it's in the system directory. Okay, so you can see decomposed part_dict. Now let's open that and have a look using vi. So yeah, it's actually the first thing in the file. So if you would like to use, for example, 8 cores, then you have to change that number to 8 and then change the number here to 8 as well. Okay, so now let's go back to the case folder and then run this command. Okay, it's finished. Now let's run the next one. Okay, so here we can see that the GATCFD is running the simulations for us using 4 cores. Okay, so this is the first time step, computing the force field, etc, etc. The second time step. So this, I think, will probably take about half an hour, so I'll pause the recording and then come back when the simulation is finished. Hello, so welcome back. It seems like the parallel simulation has been finished and there is no error messages, which is great. If you'd like to find out what exactly happened during the simulation, again, you can open up the log file, which is the gatsimple_form.log file, and it should give you a very detailed record of what happened during each of the time steps of the simulation. Okay, so okay, that was the 6th step. Now let's run the 7th one. And basically what this command does is to stitch up the subdomains into one domain, and so you can visualize the result as one integrated file. Okay, so that was finished without any problems, and then now let's run the last one. Okay, so basically what this command does is to convert the original result files, which are probably either binary or ASCII based, into a format called BTK. and then the VTK files can be visualized using ParaView or some other softwares, but ParaView is the most commonly used software, which we'll talk about in the next video. Okay, it's finished running. Now let's have a look. In fact, let's use a different command called ll to list it in this way. So now let's open the original folder we downloaded from the OneDrive storage space. Okay, so here we can see that there are only 4 folders. Okay, 0, constant, data, and system. So obviously by running this block of code, this block of commands, it's created a few other files and folders for us. So for example, the folder 523 is a time folder, so compared to the 0 folder, which stores the original conditions, the 523 folder stores the results we got, but in either binary or ASCII format, and the VTK folder then stores the results that's been converted into the VTK format. Okay, the other one that's interesting is this post-processing folder. This one has been created because when we set up the simulations, we actually put a few probes into the domain, so for each time step it would sample the results at that particular location and output the result into this folder. So now if we open the base case folder downloaded from the OneDrive storage space, which has been used to benchmark the installation and computation, here we can see that there is a folder called 522, which is slightly different from 523, but not very much. Basically, this is saying that in our example folder, the computation was finished at time step 522, whereas in this case here it was stopped at 523, but that's fine. I doubt it'll be very different. Okay, so it's also got a post-processing folder here, VTK and VTK. Okay, now let's open the VTK folder. Okay, let's open the VTK folder here as well. Okay, so it seems like the folders and files in the benchmark folder have been created in our simulation as well. So based on this information, I can say with confidence that the simulation, the installation have been successful. Okay, so obviously if you would like to go and visualize the results just so you can be 100% certain, then you can do that as well. Use ParaView, and I will talk about that in the next video. Okay, so see you next time.